Hi there. We're talking about bonding theories today. It's really called VSEPR, and I'll show you what that all means. What you should have in front of you right now is this pink sheet. I got the first two slides on there, and what you're going to be doing today is taking your notes by filling in this chart. Okay, here we go. So the valence bond theory. This is this idea that we can kind of visualize what molecules look like in real life. So we're going to take this idea of the quantum mechanic model where it's got the bubbles and the orbitals that they live in, and we're going to try to make it so a way we can picture it. Now you can see on here I've got the two alpha diagrams. So if one atom, in this case I've got oxygen, you can see at the bottom, is going to bond with another oxygen, what actually happens is these two alpha diagrams kind of like converge on each other. And they kind of make this mishmash. I know it looks complicated, but they kind of merge together. And so the orbitals, like one bubble overlaps with another bubble, and that's exactly how the covalent bond is. The bubble where electrons live for one orbital of another electron, they overlap, so electrons can fly anywhere they want. And this idea allows us to bring us to the VSEPR model. There's only one rule. VSEPR stands for valence shell electron pair repulsion. It's this idea that we're going to arrange the molecule in such a way that all of the electrons who hate each other are going to be able to get away from each other as much as possible. So when you make bonds, electrons have to be close to electrons when they overlap, but we're going to try to arrange them so they don't have to be as close to each other as possible. That's kind of the idea here. Valence shell electron pair repulsion is the theory. Okay, so here's your chart. Fill in the blanks as we go. Our whole job is to figure out how does it look in 3D. So you can see I've got here CO2. And when you look at the picture right now, CO2, it looks really linear. This is a linear shape. But I want to show you what each of these boxes mean. These are the total domains. So a domain is a region. So if you take a look at your central atom here, just your carbon, a domain is a region around the central atom. So this right here is a domain. It's the left side of carbon. This right here is a domain. It's on the right side of carbon. There are two total domains. So when I look at the left side domain, I would say it's bonded. The right side domain, it's bonded. There's a total of two bonding domains. I know that each of them have double bonds. You don't count the bonds. You're just counting are they bonded or are they not. Taking a look, I don't have any lone pairs around the central carbon. Lone pairs are these double dot things. Remember the two electron pairs? Those are lone pairs. We're only looking at the central atom though, and there's no lone pairs around the carbon. So the farthest away that all these electrons can be from each other is at a bond angle of 180 degrees. That means in this molecule, the angle from this one all the way to this one, as you can see it's a linear line, is 180 degrees. There's your first one. Let's go to the second one. Taking a look, I've got my central carbon. There are three total domains, which means there's three things around the carbon. Got that here. Are they bonded? Yes, all three of them are connected to the carbon by bonds. Three bonding domains. Do I have any double dots around the carbon? No, there are zero lone pairs. If you have a structure like this where they have three bond domains, three things bonded to the center guy, the bond angles will be 120 degrees. And if you look at it, it kind of makes sense. There's 120 degrees amongst all these bonds if it's a total of 360. So this would be trigonal planar. This is the trigonal planar VSEPR structure. Moving on to the next one. These ones get a little bit tricky. All four of these have four domains. So look at the center carbon. You can see there's four chlorines around it. That's four domains. Take a look at the nitrogen. It also has four domains. Three hydrogens and one lone pair, a double dot. But you can see it's north, south, east, and west are all covered. Take a look at water over here. Does he have something on the north, south, east, and west? He totally does. He also has four domains. So let's look at how this kind of changes what we've got going on. Gotta go to my video here. Okay. So let's look at just CH4 first. CH4, in order to get each of the bonds as far away from as possible, on paper it looks like they're all 90 degrees away from each other, but in real life it makes this sort of structure that tries to get it away from each other as much as they can. It's called a tetrahedral structure, and it has an angle of 109.5 degrees. So if you look at it in 3D, you can see it's not 90, it's 109.5 for the tetrahedral. Let's take a look at the next guy. NH3. Now you gotta imagine he's got this bubble up top. And that bubble at top is where the 2 electrons live. They actually take up a lot of space. Tons and tons of space. So much so, if you look in the video, it starts to squeeze those parts down. So that the bond angle, although it looks like it might be 109.5, it really isn't. It squeezes it so much, see it gets tighter, that it's now at a different angle, 107.3. These electrons that live up here are super big. They take up so much space, and they're strong. And they push the other atoms downward, which makes this part tighter. Think about the third one. If you took a look at oxygen, he's got this kind of bent straight structure. He's got electrons that live here. Now electrons live in humongous bubbles, and those bubbles are really strong. In other words, they're really negative. They have 2 electrons that's really negative. They are going to be able to push these other bonds even closer together. So now it's going to be 104.5 for the bent structure because electrons push so hard. Okay, so back at your notes here. Taking a look at the angles, our tetrahedral is 109.5. Hopefully you put in your trigonal pyramid is 107.3, and our bent is 104.5. Different angles because of those electron pairs pushing. If you take a look at the domains that we have, they all have 4 domains, but they do have different number of bonding domains. In the first one, 4 bonding domains and no lone pairs around the carbon. The second one, this guy right here, is 1 lone pair, and I happen to have 3 H's, 3 bonding pairs. Looking at our bent structure, it has 2 lone pairs on the north and the west side, and it has 2 H's, which are also domains, but they are bonded, so there are 2 bonding domains. So although they all have 4 things around it, the angles are different based on how many lone pairs that you have. We've got 2 more to go, and I'm sorry, I have to admit that I have been lying to you. This right here is a 5-sided thing. Take a look at phosphorus here. We know that he's got 5 dots around him. He can make 5 bonds. And I hate to break it to you, but these 2 do divorce, and they make their bonds. I told you that nobody divorces before because otherwise you just divorce all the electrons whenever you draw things, and I can't let you do that. So I had to make you think that they can't divorce, but really they can. They make this trigonal bipyramidal arrangement. You can see with the angles, it's 90 degrees sometimes, and if you look at it from this way, it's a triangle and it's 120 degrees. So our angles are that 90 and 120. So here we are with sulfur. He makes an octahedral shape because, yes, there is more divorcing. Here's the divorcing that's going on with sulfur. Every electron goes and makes a bond with somebody else, and that creates this octahedral structure. Any way you look at it, it's going to be 90 degrees. I'll turn it. You can see any time you look at it, it will always be 90 degrees. All angles are the same, 90 degrees for this one. We have 6 domains, all of which are bonding domains. So there are 6 domains, 6 bonding domains, and no lone pairs around the sulfur. There are technically more VSEPR structures than this. These are the only ones that we're going to cover. So there are ones where you can have lone pairs and 6 things around, but these are the ones that we're covering. We're on to practice time. Step 1, draw Lewis dot structures. Step 2, count the number of domains you have going around, the electron pairs. Decide are they bonding or electron pairs, and pick your VSEPR shape. I'm going to have you turn this in before the end of the hour just because I want to be able to see how you did, and we can talk more about it tomorrow. So we'll bring questions then. As a side note, because you might be wondering, do I have to memorize this? No. You will get this VSEPR structure on the test. No problems. All right, good luck to you.